Hey everyone, we're going to continue now with our look at numerical data and the summary statistics that go along with it. So let's get going here. We have ourselves, how did I do on the Chapter 1 test? How well did you do relative to your classmates? And that's kind of a good one for us to highlight here, relative to your classmates. All right, so here is a random sample of 20 Chapter 1 tests along with a dot plot and summary statistics. Okay. All right, so this is good. We've got summary statistics, we've got a dot plot, and we can just do some counting here. For example, Biff scored a 65. What is Biff's percentile? Remember that a percentile is a percent of values at or less than a given value. Our given value here is 65, so we can now just count how many are at or less than 65. Well, here's 65. We've got 2 that are at 65 and 1 that's less than 65. So that's a total of 3 out of the 20 test scores in the sample. 3 out of 20 is 0.15, so Biff is at the 15th percentile. So was Biff above or below the mean? Well, that's tough. The mean is 80. So Biff is below the mean. He's below the mean by 15 points. How many standard deviations is that? Well, the standard deviation is 10 points. So if I just do a division here, 15 divided by 10, that's 1.5. So Biff is 1.5 standard deviations below the mean. I want to take a little bit of time to kind of talk about what that means a little bit. If one standard deviation is 10 points, okay, so every time we go 10 points to the left of 80, so here's 80, we go to 70, all of these scores are less than or equal to 1 standard deviation below the mean. And all of these scores over here, these are less than 1 standard deviation above the mean. So then all the scores in green here, those are within 1 standard deviation of the mean. In other words, they're within 80 minus 70 and 80 minus 10 points and 80 plus 10 points. Okay, clearly that doesn't apply to Biff because Biff falls outside of that range, and we can quantify that just by taking that 15 and dividing by the standard deviation of 10, and that's 1.5 standard deviations below the mean. What about Marty? Marty scored an 88. What was his percentile? And for Marty, it might be easier for us to take a look at this set of test scores over here. Let's take a look at which test scores are at 88 or below 88, and that's all of these test scores. But it's probably easier just to count how many are above 88, which would be 4 out of those 20. So that means 16 out of 20 tests are at or below 88. Next here we have, was Marty above or below the mean? Since the mean is 80 and Marty scored an 88, we can easily say that Marty's test is above the mean by 8 points. Those 8 points divided by the standard deviation of 10 gives me 0.8. So we could say that Marty's test is 0.8 standard deviations above the mean. So now we have this idea of using the standard deviation as a relative distance from the mean. How many standard deviations above or below the mean? And these relative distances are really important in stats. We call that a z-score. So the z-score is defined as the number of standard deviations above or below the mean. And we could write a formula for the z-score. The z-score is, well, what did we do to get Marty's 8 points? Well, we did an 88 minus 80, and we took that whole thing and then we divided by 10. Well, okay, so what are those numbers actually, though? 88 was just Marty's value, his test value, and 80 was the mean. And then the 10, that was the standard deviation. So if I replace 88 with value, and then 80 with the mean, and 10 with the standard deviation, we get a formula here for a z-score, and that would be the value minus the mean divided by the standard deviation. Something interesting happens when we look at Biff and his z-score. If we use that same formula for Biff's z-score, we get 65 minus 80 over 10. And that's equal to a negative 1.5. And that brings us to something important with z-scores. Now, you may not think that negative 1.5 is kind of a wonky thing, but it's actually a feature. If we have a positive z-score, that means we're looking at something that's above the mean. And if we have a negative z-score, that means we're looking at something below the mean. So it's a really easy way to tell that Biff did less than average, and Marty did greater than average. So look at that as, rather than some weird mathematical curiosity, that's a feature. And it's a good thing to know whether or not you're looking at something that's above or below the mean. Now let's take a look at Goldie and his test for number 6. Goldie scored a 98 on the Chapter 1 test. Let's find his z-score. So Goldie's z-score is 98, which was his test score, minus 80, which is the mean, divided by 10, which was the standard deviation, and that gives us 1.8. That's positive, so we know Goldie's score is above the mean, and it's above the mean by quite a bit. 1.8 z-scores, 1.8 standard deviations above the mean is a lot as far as relative distances go. And so for interpretation, we just state what we just said. Goldie's Chapter 1 test score is 1.8 standard deviations above the mean. Now, if you recognize all these names, then good for you. They are from Back to the Future. And if you remember what Goldie's job, or what he was aspiring for, we get that Goldie was aspiring to be the mayor of Hill Valley. That's your Back to the Future reference. Now, there are 2 mathematical operations that are used when calculating the z-score. First, we take each score and we subtract the mean. We'll remember that the mean was 80. So what are we going to do? We're going to take this, and whatever score was 80 is now going to be 0. So after we subtract, we get these scores here. 78 becomes negative 2. For example, 80s are all zeros. Over here, 89, that's 9 above. Here's Goldie. 18 minus 80 is 18. Now, if we graphed the scores on a dot plot, we get a dot plot that looks like this. Let's go ahead and highlight. Here we go with Biff. Here we go with Marty at 88. And here we go with Goldie at 98. Now, if we just subtract 20 to get the dot plot for score minus mean, we get basically the same dot plot. Look at that. It's basically the same shape. Let's highlight again. Biff is still here at 65. Marty is still here at 88. But now Marty is at, 8 above? And Goldie was once at 98. 98 minus 80 is 18. So here's Goldie. Basically the exact same positions as before. Now, the next thing we're going to do here is talk about what happened to the shape. Well, it literally stayed the same. We basically took the dot plot and we just shoved it over to the left. That's all you do when you subtract or you add. You take the dot plot and you move it over to the left or the right. So that doesn't change the shape. The center, we just moved that from 80 down to 0. So we decrease the center by 0, and since the shape stays the same, the variability is also going to be the same. Now let's take a look at the next part. We're going to take the score minus mean, and then we're going to divide by the standard deviation. Remember that the standard deviation was 10, so now we're just going to fill out all of these numbers. This was a score minus mean was negative 19. Negative 19 divided by 10 is negative 1.9. And negative 15 divided by 10 is going to be negative 1.5, and etc., etc., etc. Now when we graph, these are our z-scores now, so when we graph our z-scores, what are they going to look like? And if you said the exact same thing, you're right. The only difference now is we've taken that distribution and we've squeezed it to fit so that the center is at 0 and most of the data is between -2 and +2. Let's highlight our 3 guys again. Well, we have Biff over here. Now his z-score is -1.5. We've got Marty. His z-score is 0.8 right over here. And then we've got Goldie. His z-score is 1.8, so he's right here. And I think it's nice if you see all 3 of these graphs together. You can see that all 3 graphs are basically the same thing, just kind of stretched and moved. So when we do the standardize these scores, turn everything into a z-score, we're not essentially changing anything about the data. We're just shifting it and squeezing it, or perhaps expanding it. So what happens to the shape, center, and variability when we divide the standard deviation? Well, the shape is pretty much the same, isn't it? The center of the distribution is still going to be 0, but what's different is going to be the variability. So for the variability, we're going to divide by 10. We divided the standard deviation by 10. So to summarize, what's going to happen to the shape, center, and variability when you add and subtract the same value A? The shape is going to stay the same. The center, we're going to add or subtract that same value A. And then, of course, the variability, the standard deviation, is going to stay the same if I add or subtract. What happens if I multiply and divide by some value B? Just like before, that shape is going to stay the same. For our measure of center, we're going to multiply or divide by that value B. And then with our standard deviation, we're going to multiply and divide by B again. So these rules here for number 8, they are the kind of rules that are easily forgotten. I can tell you from experience that a lot of students will try to add into the standard deviation when you really should never add to a standard deviation. You only should be multiplying to a standard deviation. So, number 9, let's see if we can get this. What is the mean and standard deviation of a distribution of z-scores? And that's going to be mean is 0, standard deviation of 1. The standardized distribution, which is to say the z-scores, always has a mean of 0 and a standard deviation of 1. It always has the same mean, it always has the same standard deviation. That's why we call it standardized, because it's always the same regardless of what the context is going to be. If you standardize the distribution, the mean is going to be 0, standard deviation is going to be 1. And this should bring us down to our learning targets over here. Let me clean this up just a little bit for you. And then let's do a little bit of zooming. Learning target number 1, standardized values or standardized, that's also called the z-score. Like we learned, that is the value minus the mean over standard deviation. This is a very important concept for you to get as a young statistics student. A good amount of what we do in AP statistics or in any statistics class is looking at these z-scores. So this is one of those formulas that you have to know cold. The interpretation is that whatever the context is, it is that many z-scores above and or below the mean. In interpretation, don't worry about positive and negative. If it's the z-score is -2, then you would say that whatever the context is, the test scores, for example, the test score for BIF was 1.5 standard deviations below the mean. Z-score is -1.5. Context is 1.5 standard deviations below the mean. Learning target number 2 is what happens to z-scores if we add and subtract, or what happens if we add and subtract the same number to a list of values. Well, that shape and variability stays the same, and the center is only the center is going to change. It's going to shift up and down. And if we multiply and divide by the same value b, the shape is going to stay the same, but the center and the variability will both be multiplied or divided by that same value of b. And once we get that, we can go to our Check Your Understanding section. So we have Nebel's Amusement Park in Ellisburg, Pennsylvania, has earned acclaim for being an affordable, family-friendly entertainment venue. Nebel's does not charge for general admission or parking, but it does charge customers for every ride they take. I'm assuming I'm saying that right. Nebel's, Nubbles. How much do the rides cost at Nebel's? The figure shows a dot plot of the cost of 22 rides in a recent year, along with some summary statistics. Okay, so we can use our words here. This definitely looks like a right-skewed, single-peaked distribution. So we would say the median is 1.5, and the IQR, this looks like the IQR is going to be 0.25. So suppose we converted the cost of rides from dollars to cents. We're going to basically multiply by 100. Let's describe the shape, mean, and standard deviation for this distribution. Well, we said the shape was going to stay the same. That was single peak and right skewed. The median is going to be that 1.5 multiplied by 100, so 150. And the IQR is going to be 0.25 multiplied by 100. Now this should make sense to you, because if we're saying the mean or the median is $1.50, then in cents that's 150 cents. And if we're saying the IQR is $0.25, well, then that should make sense that the IQR is 25 cents. It's the same number, just multiplied by 100. Okay, so now we're going to say that Nebel's managers are going to increase the cost of each ride by 25 cents. How would that change the shape, center, and variability? So let's remember what happened to the shape if we increase or add 25 cents. That shape is going to, the shape is going to stay the same, which is still single peak and right skewed. So the new median is going to increase. The center, let's start off with that. The center is going to increase by 25. So the median, which was 150 cents, is going to be increased by 25 cents. So the new median is going to be 175 cents. And then because we're only adding, the variability is going to stay the same. IQR is still going to be 25 cents. Question 3. Now suppose that we converted the increased cost into z-scores. What would happen to the shape, mean, and standard deviation? Well, the shape, it's going to stay the same, single peak and right skewed. because we're standardizing, the center, the mean, is going to go to 0 because every standardized distribution has a mean of 0. And then for a measure of variability, the standard deviation is going to become 1. So that pretty much does it here for our section 2.1, day 2 of section 2.1. Standardized scores, z-scores, extremely important. Really get yourself a good handle on it. Really know how to convert any score into a z-score, into a standardized score. And we'll see you next time. Have a good one. Good luck on your quiz.